Alright, today we are going to talk about propositional equivalence. So, firstly, we will introduce different terms, topology, contradiction, and contingencies. And then we will see how we prove that the proposition is equivalent to the others. Okay, so we are showing simple examples of some logical equivalence. And based on these rules, you can infer to general equivalence logic. Okay, and then we'll go to the last section, propositional satisfiability, and to see the example of pseudo. Okay, so with the original for propositions, we can assign true or false to that declarative sentence, then we can call that a proposition. In that case, it could be true or false. Alright, so if a proposition is always true, then we give a special term, topology, to that proposition. Because once you can assign true or false to this proposition, then you can see either you assign true or false to P, then the proposition, the compound proposition is always true. Because we can see P or not P. If P is true, then not P is false. True or false is true. If P is false, then not P is true. Then false or true is true. No matter you assign true or false to the proposition variable P, then the result is always true. So we call this topology. Okay, just a very special terms for this situation. On the contrary, we can also have contradiction. When you assign truth labels to the propositional variable, then the result is always false. Then we call this contradiction. So the other case is it could be either true or false. We don't know. But when you assign, for example, true for P, the final result is true. If you assign false to P, then the final result is false. Then we call such proposition contingency. Okay, so basically we are trying to give different terms or special names for these situations: topology, contradiction, and contingency. So you can see we have seen a lot of examples of contingency, right? Once we have different results by different combinations of this propositional variable, then the result is either true or false. Then we can say it's contingency. In other words, we can also say it's neither topology nor contradiction, and it's contingency. Alright, previously we have seen some examples. We can prove that two propositions are logically equivalent by its truth table. Okay, so I think this is the simplest method you can apply once you see the topic to ask you to prove if two given propositions are logically equivalent or not. Then you can use truth table. So based on the previous definition, we can see two compound propositions are logically equivalent if P then Q, or by condition of P and Q is a topology. So you can infer if P is true, then Q is true, and if Q is true, then P is also true. Both directions are true, then we can say P and Q are logically equivalent. And we have a special notations, so you can use the double arrows or 3 bars. Okay, so we use this notation most commonly, okay, to indicate P is logically equivalent to Q. Okay, and then when we need to prove that they are logically equivalent, we can examine every row of a truth table. If they are logically equivalent, then they will have the same truth values for each row. Just like we said in P then Q, we know it's logically equivalent to not P or Q. Okay, and we have seen this truth table before, right? Because you can see for every row, they have the same truth value, TT, FF, TT. Okay, that's one way we can show that two propositions are logically equivalent. Alright, next we will think a little bit further. Let's see the Morgan's law. Okay, because it's one way we can remove the parentheses of the proposition. So if we have not parentheses P and Q, then we can maybe consider we remove these notations inside these parentheses, and then we change each term a little bit. For example, once we remove not inside these parentheses, then P becomes not P, N becomes or, and Q becomes not Q. So you can consider maybe we have the impact of this negation to each element inside these parentheses. Okay, so once we have P or Q with not in front of them, then by the Morgan's law we have, if we remove this negation inside these parentheses, we have not P and or becomes N and last term not Q. Okay, because it's lost, so actually you can verify this by its truth table. Okay, so we have not, for instance, P or Q, and we have not P and not Q, and you can see the truth values agrees for each row. Okay, next let's see some key logic or basic logic equivalence. Maybe you can apply all these laws to prove during the process or during the steps when you need to prove two propositions are logically equivalent. The first law is identity law. Okay, so if you remember in linear algebra, we have the identity matrix, right? So every matrix times the identity matrix is equals itself. Right? So the concept is very similar. If we apply P and T, and the result is P or F, then the result is P. Under these operations, the result is always itself. So we call this identity laws. Okay, next one, domination law. What this word domination means? What's dominate? What's the Chinese meaning of domination? No? What's the Chinese meaning of that domination? You? Okay. 没有人知道这个字是什么 ？Okay. 哦，支配 ，right? Dominate means 就是支配了 ，OK. So that means the value is dominated or controlled by the others. If P or true, then you can see the result is P. That means the result is dominated by true false values. If we apply P and F, then the result is dominated by false. Okay, that's the reason we call this domination laws. Next one, identity laws. Okay, actually this word means if you apply 2 times 2, 2 times 2, then it will be 2 to the power of 3. So actually, this means you multiply many times. Okay. In Chinese, what's that Chinese word? Idempotent 就是幂次的，那是数学上的用语哦。If you multiply the number multiple times, it will become idempotent number. So for logic, we can say if we apply P or P, and the result is P, P or P, the result is also P. So you can say the operations apply multiple times to the variable P. So we call this idempotent loss. That's one simple double negation loss. If we apply negation for the variable P twice, then the result is 0P. And the last one, negation loss, P or not P, the result is true. P and not P, the result is false. Okay, I believe that the next 3 you have learned that during senior high school, right? We have cumulative loss, associative loss, and distributive loss. Okay, for cumulative loss, we can switch its position and the result remains the same. If we have P or Q, then it's logically equivalent to Q or P. So the order is not important. You can switch its order. So we call this cumulative loss. For associative loss, you can associate P, N, Q, and R by different orders. For example, P and Q apply first, or Q or R, you calculate this first. Okay, so we call this associative loss. The last one, distributive loss, we have P or parentheses Q and R. Then we can distribute P to elements inside this parentheses. So we have P or Q. Then we add P or R. Okay, the last one, sorption loss, P over P and Q is still P. Okay, so this is listed for your reference. Okay, next we have more logical equivalents for conditional statement and biconditional statements. Actually, you can know some of them, and maybe you can infer the others by yourself. For example, we have mentioned this, right? For the conditional statement, if P then Q, the only way to remove these errors is not P or Q. Okay, so we replace the conditional statement to the operator and or. Okay, so this is the only way. So you need to remember this very well. If P then Q, that is equivalent to not P or Q. Okay, and the next is P then Q equals not Q then not P. So we have done this before. Contraposition, right? We have reverse, inverse, and contraposition. So if P then Q, that equals to not P then not Q, or not Q then not P. Okay, maybe we can see the next, how we think this is right. P or Q equals not P then not Q. Okay, because we already know that by conditional, if P then Q, that means not P or Q. Okay, so not P means P or Q. So that's the result of P or Q. Right? So if you know the first one and the third one is definitely correct. Okay, maybe you can try yourself for the others. Next, let's do biconditional statement. The first one is from the definition of bidimensional. So we have if P is then only if Q, that means if P then Q, and if Q then P. Okay, then we also have P is then only if Q, then we have not P if and only if Q. Okay, maybe we can see this later. Alright, so from this discussion, then we can develop a series of logically equivalent forms to indicate that A is actually equivalent to B if we can develop A equivalent to A1, A1 equivalent to A2, and AN equivalent to B. Then, by this series of logical equivalence, we can prove that A is equivalent to B. That's what I'm going to do next. So, based on our previous discussion, you have seen some logical basic equivalence forms, and then we also have the Morgan's law. Let's see how we develop the process of logical equivalence. Alright, the example asks to show that not P or, for instance, not P and Q actually is equivalent to not P and not Q. Okay, so let's see the process. The first one is very simple because we have seen the parentheses, we have seen not. Okay, so this tells us we need to apply the Morgan's law, right? So the first step, we can apply the Morgan's law and we rewrite the original form. After we apply the negation into each component, then the first one becomes not P, and we transform OR to N, and then we apply not in front of the second component. Okay, not parentheses not P and Q. Okay, now we have another parenthesis with not operations. Okay, so we need to apply the Morgan's law again. Then we transform not P to P, and N to OR, and Q to not Q. Alright, so we have this one. Alright, then we can apply the distributive laws because we have N and OR here. So we have not P and P. Okay, or not P and not Q. Alright, now we have seen the basic forms. Not P and P actually is false. And then we have force or something. Okay, then we can switch its position by commutative laws. Okay, this tells us we can apply identity laws again because once we pour F itself. Okay, so in the end we have the original positions equals not P and not Q. Alright, I think you cannot remember all of these basic forms in the first place, but I think maybe after a little bit of practice, you can remember all of these laws we need to apply to prove the logical equivalence. Alright, next let's see another example how to prove the position is on topology. Okay, so let's see the answer first. We need to prove that the given position in the end is equivalent to P. Okay, that's how we prove that it's on topology. Alright, let's see the process. We have the form P and Q, if that's true, then P or Q is also true. Okay, so it's conditional statement. Like I said, we have the only way to rewrite the conditional statement by if P and Q equals not P or Q. Okay, so we have not P or Q. Okay, so after that, we can apply the Newton's law because we have negation in the parentheses. So we have not P or not Q, and we have or P or Q. So you can see, actually we have all these operations or, right? So if all the operations are or, then we can apply associative and commutative laws. So we put not P or P together and not Q and Q together. Okay, then we know by the operation laws, this one is true and this one is also true. True or true is true. So that's completely proof the original proposition case of topology. All right. Any question for this process? All right. If no, I'd like you to have the practice to prove this one is true. Okay. Please write the process how to prove P equally Q is logically equivalent to not P equally not Q. Okay, and then I'd like to ask someone later to share he or his answers on the blackboard.助教白纸。I think the first step is very confirmed, right? Because we have the only way to rewrite biconditional statement to conditional statement, right? So the first step, definitely you need to apply this one. Then you can rewrite this notation to a simplified notation, conditional statement, right? And then what's next? You have no other choice, right? Because you have a conditional statement. How to rewrite a conditional statement? You must use the equivalence form of this. Okay. So the first one, A equals A1, A1 equals A2, is confirmed. Okay, you have no other choices. Alright, so this is the first two steps to rewrite conditional statement this is biconditional statement to conditional statement. So P if and only if Q, then the only way to rewrite is P and Q. If P then Q, and if Q then P. That's the only way to rewrite biconditional statement. So similarly, if not P, if and only if not Q, then you can only write if not P, then not Q, and if not Q, then not P. Okay, then we rewrite biconditional statement to conditional statement. And the second step is to rewrite conditional statement. If P then Q, then you can only apply not P or Q as the equivalent form. Okay, so the first term is if P then Q, so we write if not P or Q. Then we have if Q then P, then we have not Q or P. Okay, and then we have if not P, then not Q, then we have P or not Q. And the last term is Q or not P. Okay, after the second step, then we have all positive variables with only and or and negation. Okay, so how to prove that this one is equivalent to this one? Okay, so maybe you need to apply maybe associative laws or distributive laws or maybe commutative laws to see if they are equivalent on the right hand side and left hand side. Okay, anyone finish the answer? I give you one extra point to show the correct answer. All right, anyone? You? Have you finished your answer?
Yeah, but my method is not as good as
That's all right. If you can prove that they are equivalent, it's all right. Please welcome to write down your answer and share to everyone.可以，
差不多。
没关系啊，你就写啊。Okay. All right. So from the student answer, you can see he's very smart because he doesn't want to transform the original type, original form into the simplified and or and negation. Instead, he just rewrite by the first definition of the conditional statement to see that the right hand side and the left hand side are equivalent. And maybe I can rewrite this process a little bit for you. to make the process A equals A1, A1 equals A2, and A2 equals A3, and AN equals B. All right? So if we run in a more formal forms, it could be, all right? This is the first one. It's a logically equivalent form. Then we have this one to show the next step. Okay, and if P then Q, what P is writing is, we can rewrite to, if P then Q, and if Q then P. That's the definition for bicondition statement. So this equals equivalent to not P if and only if not Q. Right? And then he rewrites these two terms by these two terms. Okay, so this is by contraposition, right? If P then Q, then not Q, then not P. Okay, so the next step will be not Q, then not P, and not P, then not Q, equivalent to not P. Okay, because this is what we consider as A1, but this is A, this is B. And then we write A equal to A1, and A1 equals to A2. And then we can rewrite the equivalent forms further. Okay, because not Q, if not Q, then not P. And not P, then not Q. Okay, equals not P, then if and only if not Q. So in this process, he just derived the final results directly. Okay, so if we write in a more formal forms, we will have A equals A1, A1 equals A2, A2 equals B. Then that we complete the process. Okay, so actually you can see this two is equivalent, right? Because by the definition of bicondition statement, we have if not P, then not Q, and if not Q, then not P. So that will be the definition of biconditions. All right? So actually, by this method, we have only 3 steps that we can prove the equivalence. Very good. 1 extra point and go to class F. Go to T after class. All right. The next topic is about propositional satisfiability. So let's see the definition. What is a satisfiable proposition? Okay, a countable proposition is satisfiable if there is assignment of truth values to his variables to make it true. Okay, so you need to have ways to assign truth values, true or false, to its propositional variables to make the statement true. Then we call this compound proposition satisfiable. Okay, so if you cannot find such assignment, then we call this proposition unsatisfiable. Okay. We have a equivalent form if compound proposition is unsatisfiable if and only if its negation is tautology. If its negation is tautology, that means it is contradiction. You cannot find all kinds of all combinations of assignment to make it true. Then it means it's a contradiction statement. All right, so I think this is very simple. Let's try to discover how to assign truth values for the variables to make it true. Okay, so let's take the first So, okay. Okay, let's take this for first example. If we have P or not Q, Q or not R or not P, and we add them together. So how to discover the assignment? So you can see it's very regular, right? P not Q, Q not R not P. Okay, so to make each one to be true, then maybe we can assign P is true, right? Once P is true, then the first term will be true. But we also need to, the second term is true. So Q must be true. So not Q is false, but it's okay, right? Because P is already true. True or false is also true. So once Q is true, then not R here. Then we have R in the last component. So R should be true. So not R is false. That makes the second term is also true. Right? If we have R is true, then no matter what value of my P is, then the last term is also true. So it's very easy to discover what is the assignment of truth values. Once we assign true to PQR, then we can make this statement true. So that means the given proposition is satisfiable because we actually can discover the assignment of truth values to all these variables to make it true. Okay, so I think the definition is very easy and you can try these examples by yourself. But when this proposition becomes very complicated, what is the most efficient method to discover the final answer of the assignment? What will you do? Maybe you can try true or false for each variables, but you can see once you have several terms, maybe you can find, or maybe P is true, Q is false, and you find contradiction for the major terms. So you need to try another combinations. Okay. Do you have a more promising method to discover the assignment? What's the worst case? Okay. Yeah, that's right. The worst case is you list all the truth table, all the combinations, because we have PQR, only PQR, right? So once you have only PQR, then the worst case if you list 8 rows in the truth table, then you can at least discover, you can find any combinations to make it true or not. Okay, I think that's a more promising way, better than to try it by yourself if the given position is too complicated. Okay, very good. Alright, next I would like you to compare the definitions. If you remember, we have introduced consistent system, right? And now we have satisfiable of the propositions. Do you remember who can repeat the definition of consistent system spec for me? What's the difference between two definitions of consistent and satisfiable? Okay. Okay. Anyone heard what he said? You need to assign the truth values for all system spec to make each statement true. That means the system spec is consistent. So it's all about assigning truth values for the propositions to make it true, right? Okay, so what is the difference between the definition of consistent and satisfiable. Can you compare the difference? What's the definition of consistent? Because we all need to assign those values to the position to make it true, right? Or satisfiable is equivalent to consistent. Mm-hmm. What do you say? It's equivalent. Actually, it's not. Okay.
Being consistent, no matter what values you put, it's always true. And satisfiable, it might be some it's false and some value you assign is true.
But for consistent,
It means it's always true.
no. It could be false. So if it's false, then we call this system inconsistent, or it's not consistent.
Is consistency where multiple propositions are satisfiable with the same?
That's right. Very good. Okay. Once we call that a system spec, that means you have multiple propositions, right? And you need to find a unique true-false assignment to all variables to make all propositions true. But for satisfiable problems, we only have one compound propositions. You need to discover what's the assignment to make it true. Okay, so the difference is you need to take each proposition in this system spec, make all of them true, then that will be a consistent system spec. But for satisfiable problems, you need to find the true value assignment to make this proposition true, then it will be satisfiable assignment. All right, I must give you one extra point because it's not an easy answer. All right, next let's see a special notation. When we apply conjunction and disjunctions, we can use this notation. Okay, and we have the index j is 1 to n, pj. That means p1 or p2 from the index 1 to n. So we have n terms, p1 and p2 and pn. So if we replace this notation to conjunction, then we have p1 and p2 and pn. Okay, we will use this notation for the pseudo problem. Okay, next let's see our last example, Sudoku. So can anyone explain the rules? How do you solve the problem of Sudoku? Have you played this before? Okay, I see you're nodding. What's the rules we need to complete this pseudo problem? Maybe in Chinese. You are nodding, right? You played this before. What's the rule for this puzzle? You know how to overseas there, right? You can explain in English.
So in each column and row, they are used to assign different numbers. So it's neat. So we need to see the row and column. So the actually insert same numbers. So in one row and one column, each of them is different.
Okay. Only row and column, not the rows. Okay. Yeah, that's right. In the square of 3 by 3, you can see we have 9 positions. Okay, you also need to insert the 1 to 9 into the square of 3 by 3. And each number is use only once. Okay, so you need to apply these design numbers to each row and each column and each square. Because you can see we have 9 positions for one row and 9 positions for one column and 9 positions for a square of 3 by 3. Okay, you need to insert numbers 1 to 9 to each position and do not violate the rules. The rows and columns and the squares, the number cannot repeat. Okay, that's how we solve the pseudo problem. Next, let's see if we transform this pseudo problem into propositions. Actually, we can use satisfiability problems to solve this puzzle. Next, let's see if we use P of ijn to indicate one position with number n. Okay, so we use i's row and j's column to indicate position. And this position we insert the number n. So n can be 1, 2, 3, 4 to 9. Okay, so that will be one proposition. We call that proposition because for the position ij, what number should we insert to that position? It could be a position, for example, the position 1, 1, and we put the number 6. Okay, so is the position true for 1, 1, 6? We don't know because we haven't solved this problem yet. But we can assume maybe the position 1, 1, the number is 6. Okay, so we call that a proposition. Maybe we can try if we put 6 into the position 1, 1. How do we make all propositions correct and without any violations of the 3 rules? Okay, so you can see actually we have total propositions 9 times 9 times 9 that more than 700 propositions. Okay, so we make all these propositions true without any violations. So we call this a satisfiability problem because we try to develop a very complicated propositions, make them all together, and we need to discover the truth values. Okay, we need to discover what kind of assignment of this proposition system we can find is true. If we can discover the assignment to make it true, then actually we solve the problem of pseudo. Okay, so next let's see how we develop such propositions. Okay, so once we have the definition of P of ijn, that means at the position row I column j, we have the given number n. Okay, so we can have the following positions to assert every row contains every number. So we have a conjunction from I is 1 to 9, and conjunction A is 1 to 9, and disjunction J is 1 to 9 with the proposition P of ijn. Okay, so maybe you can write down your answer, how you discover or how you understand this notation. So please write down on your paper what is okay, please expand this form into multiple terms. Do you know what I mean? You know summation, right? If summation over I equals 1 to n, and we have ai, that means a1 plus a2 plus 2an. So that's how we expand the summation notations to multiple terms. Next, I want you to write down the answer how to extend or expand these terms to multiple terms. Please write down your answer on your paper. If you remember the definition of conjunction and disjunction, we use this notation. So this is how we expand this notation to multiple terms, right? And how to expand this one? Alright. Alright, have you finished your answer? Yeah, let's write down your answer. No, we don't have P11. We have P parentheses ij. You can just write down your answer because you just replace these terms. All right. I know what you mean. All right. When we have two index I equals 1 and n equals 1, then we need to fix the first index and then loop from n equals 1 to 9 first. Okay, so this is not correct. Actually, we have, if we fix I equals 1, then first term will be 1, n equals 1, okay, and then we all different terms by looping from n equals 1 to 9 and fix the index I equals 1. Okay, so we have 1, 2, and or P1, 9. Okay, so this is the first term when we fix I equals 1. So all of this will end the other terms when we change I equals 2. Okay, so when I is 2, then we look n equals 1 to 9 and OR them together. Okay, and the second set will be n to the other set when n equals the other values. Okay, so as you can see, actually we are trying to develop the proposition systems when we have different positions that every row contains every number, and every column contains every number, and every cell contains every number. And once we have all these propositions, and we want to solve the satisfiability problems to discover what kind of assignment of IJN to make all propositions true. Okay, so conceptually, this is how we solve pseudo puzzles as a satisfiability problem. And actually, you can see this is a very complicated assignment problem because we have too many propositions. So actually, if you solve by computers, then it takes a lot of time. So we still consider this problem is a very difficult problem. All right, so that's one applications you can use propositions to solve practical applications in our daily life, such as the puzzle of Sudoku. Okay, so that's the end of this section, and we have some homework assignment for you. In this semesters, we will have homework assignment for every 3 subsections. So now we have introduced 1.1, 1.2, and 1.3. So we will have one homework assignment. So maybe next homework assignment 2 will be 1.4, 1.5, and 1.6. Okay, and I hope the questions will not too many for you. Only 5 questions in each subsections. Okay, I recommend you to write something on papers, and you can hang your home assignment at this time. Okay, so that will be the first 10 minutes when we have class on that day. Okay, because when you actually write something, you will remember it more than you typing by PDF. Okay, but if you actually want to type by LaTeX to provide these answers, it's no problem. Okay. The other thing you need to notice is we already provide the question files on course 2. For example, you can see this is homework question PDF file. So we have homework 1, chapter 1.1 to chapter 1.3. Then you need to open these files to discover what is question 2 for 18, 24. Okay, do not use your own textbook because the question will not be different. Okay, so remember to open the homework question PDF files to discover the questions. Okay, and then we have our late policy. If you have 1 day delayed, then you will receive 20% discount for your total score. Okay, that means if you delay by 2 days, the duration will be 14 discount. Okay, and then after 5 days, don't bother to submit your answer because it's already 0%. The next thing is do not copy your answer from the other students and do not provide your answer to other students. Once the plagiarism is discovered, then all students will receive 0 points. And then the last thing is the correction of scores. Once TA has finished to correct your answer and give you scores, Then if you discover anything wrong, because maybe the calculation of total scores or maybe some missing questions the TA does not discover, you can correct your score within 1 week after the homework assignment is given to you. Okay, because we have found these situations in the end of semesters and we have the final score and the student does not pass discrete mathematics and he brings all his homework assignment to the office and asks for scores from homework 1, homework 2, and homework 3. Okay, so that will be time wasting to TA and me. Okay, so please correct your answer of any scores during this semesters just within 1 week. Otherwise, you will receive your homework or midterm or final exam. 好，那看看那个这学期的作业跟考试的一些要求，同学有没有问题？还有今天上课的内容有没有我们需要再重新复述的地方？有吗？好。老师第一章还是熟悉，然后在3月17号上课那一天，前10分钟讲到到底怎么样来这样。好，那如果你真的很不想熟悉，你想要用 LaTeX 打字的话，那你可以上传到 eCourse 或者把印出来讲教也可以这样。好。You just put your paper in front of the classroom. So our class starts at 1:30. So from 1:30 to 1:45. That's the time you can submit your paper. 1:15. 好，还有什么问题？什么？可以。好，没问题的话，我们就下次上课见喽。
写在平板里，然后交上去。
写在平板里要印出来啊？
可以交 eCourse 上。
可以。
所以应该是，所以可以手写在平板上，然后交 PDF 档到 eCourse 上。可以。
然后前10分钟是上课，
就15分钟到25分钟之间。
对，超过上课前10分钟也对，超过上课后10分钟。
这个会打分数，因为我后面约在就
我们不会打分数，会当成是拉出时间。好。好。
可以写在平板里面，然后找到eCourse，还是要印出来就？
可以平板找到eCourse。好。写题号就好，不用抄。
我觉得